In this video, we're talking about how to use the second derivative test to find extrema of multivariable functions. And in this particular problem, we've been given this multivariable function f of xy is equal to x squared minus xy plus y squared plus 3y minus 1. So we're always going to follow the same process when we want to find extrema of a multivariable function. The first thing we're going to do is we're going to find first order partial derivatives of this function. So that'll be the partial derivative of the function f with respect to the variable x and the partial derivative of the function f with respect to the variable y. So if we take the partial derivative with respect to x, that means we're treating x as the variable and holding y as a constant. So the derivative of x squared, that's simple, that's just going to be 2x. The derivative of negative xy, remember that y is a constant, so that acts like a coefficient on this negative x value here, so the derivative then is just negative y. Because there's no x variable involved in the y squared plus 3y minus 1 terms, these derivatives are all going to be 0. So this then is the partial derivative of f with respect to x. If we take the partial derivative with respect to y, the derivative of x squared is 0. The derivative of negative xy will be negative x. The derivative of y squared will be plus 2y, and the derivative of plus 3y will be plus 3. The derivative of a constant, negative 1, is always 0. So now we have our first order partial derivatives. Our next step is always going to be to solve these as a system of linear equations to find any critical points of the function. So to solve this as a system of linear equations, what we want to do is set each of these equal to 0. So if we set each of these equal to 0, here's what we end up with. We'll say 2x minus y equals 0. We'll put that down here. 2x minus y equals 0. For our second equation, we're going to subtract 3 from both sides to move this constant to the right. So we'll end up with negative x plus 2y equal to negative 3. Now, if we just multiply this first equation by 2, we multiply every term in the equation by 2, then instead of 2x, we end up with 4x. Instead of minus y, we end up with a minus 2y, and 0 times 2 is still 0. So 4x minus 2y equals 0. The reason that we would do that is because then when we add these two equations together, like this, we'll get the negative 2y and the positive 2y to cancel with each other, thereby eliminating that variable, and we'll be able to solve for x. So 4x plus a negative x is the same as 4x minus x, that's 3x. Negative 2y plus 2y is 0, so that disappears. And then over here on the right, 0 plus a negative 3 is 0 minus 3, or negative 3. Then we just divide both sides by 3, and we see that x is equal to negative 1. Now, if we just plug this value for x into either of these equations, we can solve for a value of y. So let's plug it into this second equation here. So we'll have negative x, well, x is negative 1, so we'll have negative 1, or positive 1, plus 2y equals negative 3. If we subtract 1 from both sides, we'll get 2y is equal to negative 4. Dividing both sides by 2, we get y is equal to negative 2. So then when we put these x and y values together, what we have is the critical point, negative 1, negative 2. Now, if you find multiple critical points, you're going to need to use the second derivative test to test each one of them. Because we only have this single critical point, we'll just need to use the second derivative test one time to see if this is a global maximum or minimum. So in order to test that out, we're going to use this formula here for d. And this is our second derivative test formula. This value d on the left-hand side is the value we want to find. The values we need on the right-hand side are the second order partial derivative with respect to x, the second order partial derivative with respect to y, and the mixed second order partial derivative. So let's go ahead and find those 3 second order partial derivatives. We'll start with the second order partial derivative with respect to x because we're just going to take the first order partial derivative with respect to x and take the derivative with respect to x again. So this becomes partial squared f over partial x squared, which just means take the first order partial derivative with respect to x, take the derivative with respect to x again. So here we have 2x minus y. If we take the derivative of that with respect to x, we just get 2. If we take the partial derivative with respect to y of the first order partial derivative with respect to y, we took y, we're taking y again, it's partial squared f over partial y squared, taking the derivative of negative x plus 2y plus 3 with respect to y again, the derivative of negative x is 0, the derivative of 2y is 2, and the derivative of 3 is 0, so we just end up with 2. And then if we want to find the mixed second order partial derivative, that'll be partial squared f over, let's use the first order partial derivative with respect to x and take the partial derivative with respect to y. So then we would have partial x, partial y. But remember, we could also start with the first order partial derivative with respect to y and take the derivative of that with respect to x. Either way, we should get the same answer for the mixed second order partial derivative. But starting with 2x minus y and taking the derivative with respect to y, the derivative of 2x will be 0, the derivative of negative y will be negative 1. So that's going to be the value of our mixed second order partial derivative. Now all we need to do is plug these values into our formula here for d. So we get d is equal to the second order partial derivative with respect to x, we found that to be 2, so we're going to get 2 here. The second order partial derivative with respect to y, which we also found to be 2 right here, so we multiply those together. Then we subtract the mixed second order partial derivative squared. So we take negative 1 and we square it. And the value we get for d is going to let us classify the critical point that we found. So what we see then is that we'll call this d of negative 1, negative 2, because we're evaluating this critical point, negative 1, negative 2, is going to be equal to 2 times 2 is 4, minus negative 1 squared is 1, so we end up with minus 1. That's going to be equal to 3. Now keep in mind that when we took our second order partial derivatives, we got constants here, so we could just plug those into this formula for d. But sometimes your second order partial derivatives are still going to include variables, x and or y. In that case, what you need to do is take the critical point that we found, negative 1, negative 2, and plug those in for the variables. So for example, if we had ended up with 2x here, we would have wanted to plug in negative 1 for x to get 2 times negative 1 is negative 2, and then we would have plugged negative 2 into our formula. So if you got variables in your second order partial derivatives, just plug in the critical points, and then you can say that this is d of the critical point and find this value here. So we said that d at this critical point was 3. So by definition, if the value that we find for d is less than 0, d less than 0, we can say that the function has a saddle point at the critical point that we were testing. If d is equal to 0, then the second derivative test is inconclusive for that critical point. If d is greater than 0, then we actually have to look at the second order partial derivative with respect to x to determine whether or not we have a local maximum or local minimum. So if d is greater than 0 and the second order partial derivative with respect to x is also greater than 0, then we're looking at a local minimum. If d is greater than 0 and the second order partial derivative with respect to x is less than 0, then we're looking at a local maximum at that critical point. So for us, we can see that d is equal to 3. 3 is greater than 0, so then we can tell that we have to look at the second order partial derivative with respect to x. If we come back here to the second order partial derivative with respect to x, it's also greater than 0. So for us, that's this third case right here where both are greater than 0. And that tells us that we have a local minimum. So then we can say that negative 1, negative 2 represents a local minimum for the function. But because this is the only critical point, we can say that negative 1, negative 2 represents a global minimum for the function because this is the only point at which the function changes direction. So negative 1, negative 2 is a global minimum of this multivariable function, and that's how you use the second derivative test to find extrema of a multivariable function.